Rahim. Welcome to the second lecture of our course. In this lecture, we are going to talk about the linear elastic single degree of freedom system. We go through it. Okay, so let me just give you an example of a simple structure like the elevated water tank that can be idealized as a concentrated or a lump mass supported by a massless structure that only provides the stiffness. For example, let's say this is a water tank, overhead water tank. And it is supported by this massless column. The column is not massless, but if you compare the mass of the column with the mass of the tank here, so it's less than that, that's why you can ignore its mass. So we assume that this is a massless column. And we assume that this is lump mass. So this overhead water tank can be considered as a lump mass or a concentrated mass in case when the tank is full. Okay, so a system like this can be considered as a single degree of freedom system. We have to also look at the fact that the damping must be included. Okay, and this will basically take into account, this will account for the energy dissipated during the vibration of the structure. So damping must be included to account for the energy dissipation. During vibration of the structure. Okay, we can also consider a single story frame structure as a single degree of freedom system. Okay. For example, if we have a one bay and one story frame like this, okay, let's assume that the lateral stiffness of these columns is K. This frame floor mass can be considered as a lump mass at this level. This is M here. And since we have to take into account also the damping of the system, so let's make a mechanism that is taking care of the available damping capacity in the structure. Okay. we will see that this damping is represented by a coefficient C, a viscous damping. Okay, so again, it's also an example of an SDOF system. Now, during an earthquake, what happened is that the ground move. There's a ground motion that we all know. So what happened? We just change this color. If the ground move by an amount UG, so what happened is that let's say this is if the structure move rigidly, so this will be the new position. But what happened is that the base of the column moved to that point and it deflects like this. So the lateral movement also induced lateral deformation in the system. So the same way this column will also deflect like this, okay? And this is how it will move, okay? And the mass will move to a new position here. Okay, now if you look at here, let me just change the color now. If you look at this here, this is basically the relative deformation which is taking place in the column. And from here up to here is basically the total deformation or the total displacement that include the ground displacement plus the relative deformation in the member. So what are the property of this SDOF system? There is a mass concentrated at the top, so it has a concentrated mass. Okay. The massless frame provide lateral stiffness to the system. So we assume that the columns, they are massless, and also the beam, so we assume that this is a massless frame. But it is meant for providing lateral stiffness. That we represent by K. And also there is a viscous damper or a dash part which is defined by a damping coefficient C. They dissipate the vibration energy of the system. So actually there is no damper in the structure system, but actually if the structure vibrates, it dissipates energy. So in order to show some mechanism for that, how that energy is dissipated by the system, which is basically inherent in the system, so we use the dash part or the viscous damper to represent that energy dissipation capacity of the system. So even last time we discussed that the governing equation for the structure deformation, let me just mention here, equation governing the structural deformation or displacement of the mass relative to the ground can be written as mass time acceleration plus c into velocity plus k u, that is equal to minus m, the acceleration with that of the ground acceleration, which is varying with time. So this is how we can write the differential equation that describe they describe the equilibrium of the dynamic system, and this can be solved in order to obtain the response history of the displacement. We call this system as a single degree of freedom system because the motion of the system can be described by a single displacement. Therefore, it is called as a single degree of freedom system. Now, in the system, if in this equation for the single degree of freedom system, mass and stiffness can be calculated from the dimensions of the structure and the sizes of the structure elements. So it can be calculated. Now, damping cannot be calculated from these structural properties. Okay. So what we do for damping, basically the free vibration test or the harmonic vibration generator experiments on actual structure provide data for determining the damping ratio at small amplitude of motion. So what we have here, the free vibration test, and there are a number of techniques how to do the free vibration test. And the harmonic vibration, generator. So there is also an eccentric mass system or eccentric mass vibrator here in our department that can be used for the system identification, for reading the damping of the system, as well as for reading the natural vibration frequencies of the system. Now, if we use the system identification methods applied to the structural motion recorded during earthquakes, it will lead to damping ratios values at the higher amplitude of motion. So what I want to emphasize here that during actual earthquakes, if you record damping or if you record other parameter like the frequency and vibration period, we will talk about this in a minute. So those are basically obtained at the higher amplitudes. So earthquake lead to properties or values at higher amplitude. at higher amplitude of motions. So when the amplitude of the motion is high, so in that case, the value that we obtain cannot be called as the initial values and cannot be called as the elastic values, because there is always some nonlinearity. Now, if we look at that same equation and if we divide that equation by mass, so the equation will change to this form: acceleration plus 2, the term for the damping coefficient, omega in the natural frequency, circular frequency, plus omega n square deformation is equal to minus the ground acceleration varying with time. This is what we can get. Now, this equation, you can see that the equation of motion now is in terms of two structure, mainly two system parameters. One is the omega, which is equal to square root k by m, and the damping ratio, that is equal to basically the damping is a ratio of the critical damping of the structure. Okay. Now let's talk a little about the system parameters. So these two system parameters, the omega n and the damping, they are known as the natural circular frequency n is a subscript because it's natural. Circular frequency of vibration which is in radians per second. And the damping ratio now also the related to omega n is the actual period of vibration of the system that is defined as the time required for the undamped system to complete one cycle of motion when vibrating freely without the external excitation. Okay, and this is denoted as Tn. Okay, the unit is in second, and it is related to omega n is Tn is equal to 2 pi omega n. So here we assume that the system is undamped. Undamped system. And we also assume that it is vibrating freely without external excitation. There is another parameter that is related to the system properties. For example, the system executes one by Tn cycles in 1 second. Okay? This natural cyclic frequency of vibration is denoted by Fn. This is denoted by Fn, which is equal to 1 divided by Tn, the natural vibration period. And the units of this parameter is hertz. Now, the term natural frequency of vibration, generally when we say natural frequency, so we means omega n and Fn. So these both are natural frequencies. Natural frequency. So it's either circular or cyclic, but both are called as the natural frequency. Now, the natural vibration properties, the omega n, Tn, and Fn, depend only on the mass and stiffness of the structure. So omega n, Fn, Tn, which are exactly, they provide exactly the same information. They all depends on mass and stiffness. Now, as I mentioned, the qualifier natural that we are using, natural frequency or natural vibration period, is used in defining, basically to emphasize the fact that these are natural properties of the system when it is vibrating freely without any external excitation. Remember that they are valid when the system, for a system vibrating within its linear range of behavior. So when the behavior is linear. So if you look at the equation here, this equation, so we can see that given the natural vibration period or the natural frequency and damping ratio of the system, the deformation history, the deformation history is found to a specific ground acceleration here. So given the omega n damping ratio and the ground acceleration, you can obtain the response for the displacement. So I will not go into those solutions because they are probably you already studied it in the dynamics. So let's talk about the earthquake ground motion, because if you look at the equation here, so we have the ground motion on the right hand side. There are some of the characteristics and properties of the ground motion that we should understand. Now, for engineering purposes, the time variation of ground acceleration is the most useful way of defining the shaking of the ground during an earthquake. So this is what we all know. When an earthquake occurs, it's not just a single value, but it's basically a series of values which is varying with time. So what is important is the time variation ground acceleration. So where these ground accelerations, it comes from instrument known as strong motion accelerogram. So let me mention here a strong motion accelerogram records 3 components of ground acceleration. Okay, so it records 3 components, 2 horizontal, which are orthogonal, so 2 orthogonal components of the horizontal motion, and 1 vertical. So 2 horizontal and 1 vertical. Okay, so the horizontal may be sometime east, west, north, south, or with some, or defined with some angles. Let me show you an example of a acceleration time history recorded during an earthquake. Okay, so this is an example that shows the north-south component of the ground motion recorded at a site in El Centro, California, during the Imperial Valley earthquake of May 18, 1940. You can see here. Now, if you look at the acceleration here, you will see that ground acceleration varies with time in a highly irregular manner. Okay? Now remember one thing, that the ground motion always, for example, if we record like this, we presume to be known and independent of the structural response, implying that the soil structure interaction is not included. Okay, so for example, the instrument is located in such a place which is not taking into account, which is not incorporating the structural response, but it's only the ground response that is recorded during the earthquake. Okay, now what you see here is the ground velocity, and here you see the ground displacement, which are computed by integrating the ground acceleration. So these are also important because sometimes it's important to understand how much peak velocity and how much peak ground displacement is there for a structure as a demand. Now, the earthquake accelerograms, they are digitized and processed, and the process record is then defined by numerical values and discrete time instants for dynamic response analysis. If you look at this, so earlier in the past, these accelerograms were recorded by a drum and a pin with traces. But these days, in modern days, you can find digitized record, which give these acceleration as a function of time, well, like changing with a very small increment or very small instance of time, in order to define this as accurate as possible. Now, the time instant should be closely spaced to describe accurately the highly irregular variation of acceleration with time. So if you look at this jagged accelerogram and this variation which is taking place at very small fraction of time, so you should try to make the time step such a way in order to accurately simulate this accelerogram. Typically, the time interval is chosen to be 1/10th. So if I mention here, let me mention here. So the time instant here for accelerogram like this is typically 1/100 to 1/50. So this is the fraction of time that is used as a sampling time to describe an accelerogram. So sometimes you may need like 1500 to 3000 points to fully describe the ground motion. So you need very large points to describe the ground motion. As I mentioned that the ground velocity and ground displacement, they are computed by successive integration of the acceleration time function. Now remember that because of the integration process, the accurate velocity and accurate displacement, the accurate determination is difficult, okay? Why? Because whenever we are processing accelerogram, so what we do is that let me just go to the other slide. Okay, for velocity, and displacement, the accuracy, it's not always accurate because of the fact that long period components of motion are usually filtered out during record processing. Okay, so whenever we do signal processing or processing of the accelerogram, so we apply filters, band filters. So mostly we remove the long period components. So that can affect velocity as well as displacement. Also in the past, there were analog instruments, analog accelerographs, which had the problem like they did not record the initial part of the ground motion, because to trigger the analog accelerogram, you need some amount of or some amplitude of ground motion. So it cannot measure very low ground motion, but if it is higher from certain level, then it start recording the ground motion. Okay, so they are basically triggered at some higher ground motion, so it cannot sense the ground motion, which is the motion intensity less than the motion intensity required to trigger the analog accelerogram. Okay, so they are triggered at certain amplitudes. Okay. So for the analog accelerogram, the baseline or the zero acceleration is unknown. You do not know for sure which is the zero acceleration. Now, the modern digitized or the digital accelerometer overcome this problem, the second problem, by providing a short memory so that the onset of motion is measured. Okay, so digital accelerometer overcome this shortcoming. Okay, now let's talk about the response history. Ground acceleration during earthquakes varies irregularly to such an extent that analytical solution of the equation of motion must be ruled out. For example, if you look at this kind of acceleration demand, which is defining the right side of the equation, you cannot solve analytical equation for this very highly irregular acceleration demands. So analytical solutions are ruled out. Okay. So for a given ground acceleration, let's say that is defined as UGT, the deformation response UT of the system depends only on the natural vibration period of the system and the damping. Okay, so we can say that this UT depends on the natural vibration period and the damping ratio of the structure system. Okay, let me show you an example. Okay, this is an example that shows the deformation response of three different systems to ground acceleration at El Centro, California. Okay, so here what you see is the time variation of the deformation on the y-axis, okay, and time on the horizontal axis. And here you see that this deformation history is for a SDOF system. There is a time period of 0.5 second and damping of 0.02 or 2%. One second and the same damping. And this is another system. There is a time period equal to the vibration period equal to 2 seconds and the same damping. Okay, so what is changing? Only the vibration period of the SDOF system is changing. And you can see that because of that change, there's a huge change in the history of the deformation. Okay, so like the peaks are varying as well as their variation is, or their trend is varying. Okay, on this side, if you see here, there are cases where you see that the vibration period is constant, it's 2 seconds, like this case, but the damping ratio is changing, 0.02 and 0.05. So again, with the change in damping ratio, the trend of the deformation is changing as well as the peaks are changing. Okay? Now it is observed that system with the with same damping respond, the system with more damping respond less strongly than to lightly damped system. So if the damping is more, you can see that it's respond less strongly as compared to the system which is less damping. Now, if we know the deformation response history by a dynamic analysis of the structure, the internal forces and stresses at each time instant can be determined by static analysis of the structure subjected to the equivalent static force. Okay, so for any instant of time, we can get the deformation, and for that deformation, we can obtain the corresponding internal forces and stress in the structure, and we can analyze the structure statically. Okay. For example, the force acting on SDOF system, Fs with time, can be obtained by multiplying stiffness by the deformation. Or we can write the same as a function of mass omega n square and then the deformation. Or we can also write this as mass time acceleration. Okay, but remember that acceleration this is basically the pseudo acceleration, which is equal to omega n square into the deformation that you obtain. So if you obtain the deformation history, take the value, multiply that with omega n square, you get the pseudo acceleration. Multiply that with the mass, you get the static force acting on the single degree of freedom system. Okay, and in particular, the base shear and the base overturning moment can be obtained. So there is a parameter base shear, written as VBT, and base overturning moment, MBT. Okay, so they are obtained as VBT is equal to M times the pseudo acceleration, and MBT is obtained as height times the base shear. Okay, for example, if you look at a single degree of freedom system, a single story frame, let's say this is the height. Okay, let's say this is the stiffness based force FST acting on the system. So this is the base shear acting on this SDOF system, and this is the corresponding base overturning moment acting on this single story frame. Remember that in the base shear, we have the pseudo acceleration times the mass, not the mass times the total acceleration. Now, response spectrum. So what is the concept of the response spectrum? The complete history of any response quantity can be determined by the numerical procedure or by the numerical or the time history analysis that we just mentioned in the previous example. However, for the design of new structure or the evaluation of existing structure, it is generally sufficient to know only the peak value of response. Okay? So what we are interested in the peak value of response. Or we can say peak response. And this peak response is defined as the maximum of the absolute value of the response quantity. So for example, if I'm mentioning here the peak response for a given response quantity R naught is equal to the maximum over time of that same quantity varying with time. The absolute value. Now, if I plot the peak value of this response as a function of the natural vibration period of the system or a related parameter like the circular frequency or the cyclic frequency, that plot is called as the response spectrum for that quantity. Okay, so a plot of R naught as a function natural vibration period is called as the response spectrum. Now, each such plot is for a single degree of freedom system. They're having a fixed damping ratio. And if you want to develop several such plots for different values of damping, that will cover the range of damping values encountered in actual structures. Okay, so if you remember that in the previous, when we were talking about the history, so we mentioned that Husner was instrumental in the widespread acceptance of the concept of the earthquake response spectrum that was introduced in 1933 by Biot, and which you can see is now a central concept in earthquake engineering. So Husner, and in 1933 by Biot. Okay? So Husner simply extended the work of Biot and presented the concept of the response spectrum. So this is the concept. Now let's discuss the various response spectrum that we can develop for structure and that we use in the design and the analysis. So the first one is the deformation. Response spectrum. Which we also call as displacement response spectrum. Now this is basically a plot of the peak deformation. So this is basically a plot of the peak deformation. D there is plotted as a function of the natural vibration period of the system. Is a function of Tn. Okay? Let me show you an example. This example shows the procedure to compute the deformation response spectrum. So what you see here is the ground acceleration. And then you see here the time variation of the deformation of three SDOF system with different periods, but the same damping ratio. Okay, so the time period for the vibration period for this is 0.5, it's 1, and it is 2 for this, while the damping ratio is 2% for all the three. But you can see that they are behaving differently. Now what we do is basically for each system, the peak value of the deformation is determined from its response history. Okay, so you pick the highest amplitude of displacement, highest amplitude, highest amplitude. Now the D value or the peak response value for deformation so determined for each system provides 1 point on the deformation response spectrum. For example, if you look at this 1 point here, 2.67, it comes from this response history. 5.97 comes from this response history. And the 7.47 comes from this response history. If you repeat such computation for a range of values of vibration period, while keeping damping constant, it will provide the deformation response spectrum as shown here. So this will be a complete response spectrum for a single ground motion, okay, for SDOF system with varying time period and constant damping. Okay. Next is the pseudo response spectrum. Pseudo velocity response spectrum. Now let's consider V for an SDOF system with natural frequency omega n related to its speed deformation d by the equation V is equal to omega n d. Okay, we can also write this as 2 pi divided by Tn d. Now this quantity V has a unit of velocity. If you look at the unit, this is meter, this is second, so it's like a meter per second or centimeter per second or feet or inches per second. So this has a unit of velocity. Now associated with this velocity is also the kinetic energy of the structure system or the structure mass that is equal to the peak value of the strain energy, stored in the system during the earthquake. So how much energy is stored in the system is equal to the half mv square. The pseudo velocity response spectrum is basically a plot of V as a function of the again as a function of the vibration period Tn or natural vibration frequency of the system. Okay. Next is the pseudo acceleration response spectrum. Now consider a quantity A for an SDOF system with natural vibration frequency omega n related to its peak deformation with this equation, which can be also written as 2 pi divided by Tn d. Now the quantity A has a unit of meter per second square or feet per second square or inch per second square, like the acceleration. Okay? It is related to the peak value of the base shear or the equivalent static force. So as we mentioned earlier, that the peak force, peak static force or the peak base shear of each system depends on the mass and the peak pseudo acceleration. Okay? Which we can also write as a function of A by G into W. Where in this equation, W is the weight of structure and G is gravitational acceleration. Now remember that the peak base shear is equal to the inertia force associated with the mass undergoing acceleration A, not the true acceleration as the like the one that we obtained while discussing the response histories. So A, but not total acceleration like this, okay? So during the base shear computation, we use the pseudo acceleration and not the response acceleration. If you look at the function, the term here, when the base shear is written in A by G into W, A by G may be interpreted as the base shear coefficient. So this is called as the base shear coefficient. Okay, base shear coefficient. Or the lateral force coefficient. Base shear coefficient or the lateral force coefficient, it's basically used in building code to represent the coefficient by which the structural weight is multiplied to obtain the base shear. So for example, this number you may get is 0.05, 0.1, 0.15, 0.2, and so on. So it's like the friction or the final base shear like may becomes like 0.1 W. This is the lateral force that we apply on system. So the lateral force that we apply becomes fraction of the weight of the structure. The pseudo acceleration response spectrum is a plot of A as a function of the natural vibration period Tn, just like the deformation and the velocity. Okay, so welcome back. Now this is the response spectrum for the El Centro ground motion during the Imperial Valley 1940 earthquake. So here you see is the deformation response spectrum. As we mentioned that this is the way how to construct the response spectrum. And then using the equations, as we just mentioned here for the velocity, to multiply the deformation with the 2 pi over Tn, and for the acceleration, to multiply the same with the 2 pi over Tn power 2. So this is what you can obtain. So this is what you see here is the pseudo velocity response spectrum. And for the same ground motion, you can have the pseudo acceleration response spectrum. Okay, and if you see that all the three have different shape, but they essentially provide the same information and will result in the same demand in the structure, no matter if you are using displacement or if you are using velocity or if you are using the acceleration, because all these three are always related to each other. Now let's talk about the combined DVA spectrum. Okay, so each of the deformation, pseudo velocity, and pseudo acceleration response spectra for a given ground motion contain the same information. So, as I mentioned, that there is no more, no less difference, they are exactly the same. The three spectra are simply different ways of presenting the same information on structure response. Knowing one of the spectra, the other two can be obtained. So, for example, using the simple relations among the three deformation, pseudo velocity, and the pseudo acceleration, response spectra make it possible to combine these into a single plot on a four-way logarithmic graph paper. So you can combine DVA response spectrum into a single plot. Okay, there is on a four-way logarithmic graph paper, which you can use to read all the three quantities directly from the same plot. So what are the properties of these DVA spectrum or this single plot, which is plot on a four-way logarithmic graph paper? The vertical, the vertical and horizontal scales, like the vertical is for the velocity, and the horizontal is for the natural vibration period. And these are the standard logarithmic scales. So for example, if this is the way of the scale, just the how it look like. So Tn is on the x-axis and the pseudo velocity is on the y-axis. The two scales for d and v, so how we represent d and v on this plot. D slopes at a positive 45 degree, and A, or the acceleration, sloping at the minus 45 degree to the Tn axis. And they are also logarithmic scale, but not identical like Tn and the V. So there are, like you can make lines of 45 degree. You can make a scale at a 45 degree for displacement and a scale at a 45 degree for acceleration. Okay, so for example, if you have a spectra that looks something like this, okay, this is what you can plot on this four-way plot, because there's one scale for Tn, one for the V, and one for the acceleration and the other for the displacement. So this one is for the displacement, or D you can write, and this one is for the you just mentioned here, this one is for the acceleration A. So at any point on this plot, for example, if you go there at a given time period, so at a given time period here, at a given vibration period, this will give you velocity on this plot. So this what you can get velocity at that point. If you draw perpendicular on this, it will give you acceleration, and if you draw perpendicular on this, it will give you displacement. So when we are drawing this combined DVA spectrum, what we do is that the V velocity and the vibration period data, they are plotted on the logarithmic plot, and then for reading displacement and acceleration, these lines are added at 45 degrees. For a given natural period Tn, the D and A value can be read from the diagonal scale. So these are at the diagonal 45 degree. Okay. Now let me just give you an example that how those three response spectra, the acceleration, velocity, and displacement, can be combined to have a combined DVA response spectrum for an earthquake. Okay, so this is the same record that you see here. So here you see velocity on the y-axis and vibration period on the x-axis. Okay, and these are the diagonals. So this is for the acceleration and this is for the displacement. So for this plot, you can see that it is reading displacement of 7.47, acceleration of 0.191 g, and velocity of 23.5 from here. So this is like a very convenient way of looking at all the response quantities, just reading all the response quantities from one plot. Okay, now what is a response spectrum? So a response spectrum should cover a wide range of natural vibration periods and several damping values so that it can provide the peak response of all possible structures. There are other concepts known as spectral regions. So spectral region on the response spectrum, they're also important to understand. Let me show you an example. Okay, so this is one of the example of the combined DVA response spectra for an earthquake, for a central ground motion, having a damping value of 0, 2, 5, 10, and 20. Okay, and if you look at the range of the vibration periods, we start from a very small value like 0.02 up to 50 seconds. So it is covering a huge range of vibration period and also a significant range of damping 0, 2, 5, 10, and 20. So this is like a complete response spectrum in terms of the DVA response, which you can use to read the response of any single degree of freedom system, knowing the vibration period of the system and the available damping in that system. Now, we are talking about the spectral regions. So let me show you another plot here, which you can see. This is as an example that shows one of the spectrum curve for 5% damping together with an idealized version that is shown by a dashed line. Okay, and both are plotted using the normalized scale. If you look at the velocity, it is normalized by the peak ground velocity. If you look at the displacement on this diagonal, it is normalized by the peak ground displacement. And if you look at the acceleration on this diagonal, that is normalized by the peak ground acceleration. The acceleration, pseudo velocity, and the deformation axes have been normalized, as you already know. Okay, and these values, uh, UGO is the peak ground displacement, UG double dot is the peak ground acceleration, and UG dot is the peak ground velocity. Now, if you look at this jagged line, this shows the response of various single degree of freedom system having a damping of 5%. Okay? And when you look at this complete range of spectrum, you can identify various regions. But for that, what you have to do first is to idealize them. Okay? Idealize the jagged lines with those dashed lines, with the light dashed lines. Now, if you look at the spectrum for the time period, for the vibration period less than TA, this is TA, 0.035. And this is the vibration, the vibration period or the range where the vibration period is less than TA, the peak pseudo acceleration approaches the peak ground acceleration. We look at this dashed line here, this one. It is drawn perpendicular to this line at a point of the peak ground acceleration of the ground motion. So it is a straight line going this way, and this from the actual record, if you draw this slope, it intersects the line at this point, and beyond this point, the the response acceleration is exactly equal to the peak ground acceleration. So this is one of the property that you can see from this plot. Next, for system with very long periods, for example, for Tn greater than Tf, this is Tf 15 seconds. So if the time, the vibration period is beyond 15 seconds, so what is happening? The peak deformation approaches the ground deformation. Now, here is a line that you can see here, which is drawn perpendicular to this diagonal straight line at the peak ground displacement, which approaches the response displacement when the time period is larger than 15 seconds. Now, for short period system with the vibration period between TA and TC, for example, this is TA, this is TB, and this is TC. So it's like a sloping region. In this region, from TA to TC, the pseudo acceleration is more than the peak ground acceleration. Okay, because this line represents the peak ground acceleration. So if you see, it is increasing, and then you can see that somehow it stabilizes, because this is also idealized as a straight line. So now this increase is equal to the amplification that depends on the vibration period and the damping. Vibration period, because as you start moving from TA, the factor is started to playing a role. It is increasing, but then a time comes that it becomes constant. So how much is the amplification depends on the vibration period and the damping ratio. So currently we have the value for the 5% damping. If you take other damping, 2% or 10% or 20%, then that amplification will be different. Over a portion of the range, right from TB, from here to TC, A may be idealized as a constant. So you can see that this is a constant acceleration. You can see that there is no change in acceleration as you move from TB to TC. Okay, because it's just a single slope line that is perpendicular to this line. So it is just reading one acceleration value. So it is constant and it is equal to the ground displacement amplified by a factor depending on the damping. Now here the acceleration is not depending on the time period, is not depending on the vibration period, but it's only dependent on the damping. So it does not depend on the vibration period in that region. For long period system with Tn between Td and Tf, so this is Td and this is Tf. This region is a long period range. The deformation generally exceeds the ground displacement, which is true. This is the ground displacement, and the ground displacement is more in that region. And again, with the amplification factor depending on the vibration period and the damping. So you can see that there is a linear slope. Okay? But there is also a portion between Td and Te where displacement can be considered as a constant at a value equal to Ug. For intermediate period system, for example, between Tc and Td, velocity may be idealized as constant, where the value is equal to the peak ground velocity amplified by a factor depending on the damping. Okay, so you can see that there is a amplification, there is a constant amplification that depends on the damping and does not depend on the vibration period. Now from this plot, the greatest benefit of the idealized spectrum is in constructing a design spectrum representative of many ground motions. Okay, if you look at this jagged line, it will be difficult to read, but if you look at the idealized one, it is very easy and conceptual to read for the design and assessment of structure. So it is logical to divide the spectrum into 3 period ranges. The long period range when Tn is greater than Td, which is called the displacement sensitive region. Look at here. From this Td onward, this region is displacement sensitive region because the structure response is related most directly to the ground displacement. Okay? And then there is a short period range for Tn less than Tc, so right from this up to Tc, this region is called the acceleration sensitive region because structure response is related most directly to ground acceleration. The intermediate period range from Tc to Td is called the velocity sensitive region because structure response appears better related to ground velocity than other parameters. Now, the spectral regions, the acceleration sensitive, velocity and displacement, and also these period values Ta, Tb, Tc, Td, Te and Tf, which is separating these regions, depends on the time variation of the ground motion, in particular the relative values of p ground acceleration, velocity and displacement. Okay, so these values, they are not constant, but they are dependent on the acceleration time history. These ground motion characteristic depends on the earthquake magnitude. Okay? So the time history we know depends on the earthquake magnitude, fault to site distance, source to site geology, and the soil condition at the site. So all these, like the soil condition, source to site geology, the fault to site distance and the earthquake magnitude, they all affect these values. Also, the near fault ground motion often contain long period pulses, which can also have different shape of the design spectrum. Let's look at the example. This is an accelerogram that is recorded for Northridge earthquake in 1994, which is a fault normal component of the horizontal ground acceleration recorded at one of the stations in California. Now, if you look at here, the ground velocity and ground displacement, which are computed by the integration, you can see a clear pulse in the acceleration, also a clear pulse in the velocity, and also the same is visible in the displacement. These are the near fault ground motions which can have impact on the design and assessment. In this example, what you see is the fault normal component. As I mentioned, it was in a station located towards the direction of the fault rupture. That's why we call them as fault normal. So what is evident is a long period pulse in the acceleration history that appears as a coherent pulse in the velocity as well as in the displacement history. Such a pronounced pulse does not exist in ground motion recorded at locations away from the near fault region. Now, sometimes there is a ratio of the peak ground velocity to peak ground acceleration and a peak ground displacement to the peak ground velocity. They are very different for the near fault region and for the distant regions. And as a result, the response spectra for near and far fault motion are very different in shape. Okay, let me show you an example. So this is an example that shows the idealized version of response spectra for one far fault motion and the fault normal component of three near fault motions from earthquakes of similar magnitude. Okay, if you see, this is a tuft record or component for the tuft earthquake, which is a far fault ground motion, and then you see these three cases for, I think, Kobe earthquake, Loma Prieta, and Northridge, that is showing you the ground motion recorded in the near fault region. So comparing these indicate that the velocity sensitive region is much narrower for a near fault motion, and their acceleration and displacement sensitive regions are much wider. If you look at the near fault ground motion, their velocity region is very narrow, but their displacement and velocity region is wider as compared to the tuft record. So this is what is the effect of the near fault region. Now, talking about the elastic design spectrum, a design spectrum differs conceptually from a response spectrum in two important ways. Number one, the jagged response spectrum is a plot of the peak response of all SDOF system, and hence is a description of the particular ground motion. So, for example, this is just for one ground motion that you saw. Be just like this. You can see this is a jagged response, but just for one record. The same as this is just one record for different damping. So these jagged response that you see here is just for one record. Okay, so response spectrum and elastic design spectrum has this different, that response spectrum is just for one earthquake. One ground motion. So it's only the description of a single ground motion. On the other side, the smooth design spectrum is a specification of the level of seismic design forces. Okay? So smooth design spectrum or the elastic design spectrum it specifies the level of seismic design force or deformation. So it's not basically a response spectrum, it's not a response, but basically it is specifying the level of design forces or deformation for a structure. Okay? We says the elastic design spectrum is relatively smooth. Let's see this. If you remember, this is the response spectrum for a single record. So you can see how much jagged it is. And this one that you see here, wait, this is again another, this one. Okay, so here you see this black line here and the dash one, and then the other black one. So this black spectrum here, this curve, is a mean curve for many ground motion records. So analyzing a number of ground motion records and then taking the mean of it gives you this spectrum, which is fairly smooth, and you can very easily idealize them as a smooth elastic curve. This one is the mean plus one standard deviation, because when you are analyzing a number of ground motion records, so you will see that there is a variation. Okay, so that variation can be taken into account by considering mean plus one standard deviation or mean minus one standard deviation. So minus is not that important, but the plus is important because there the demand is higher. So you can go even up to mean plus one standard deviation, where the probability of mean is 50%, but therefore the mean plus one is about 84%. Okay, now as I mentioned, that the design spectrum recognize the ground motions at a site. Like in this case, this spectrum is not for single record, not for single ground motion, but for so many ground motions. And remember that the ground motion is not having just a single source or the fault to site distance, or not a single magnitude, but it is for a variety of magnitude, for a variety of distances. Okay, and but considering the same damping, considering the same site, but the source to site geology can be different. So this is what the differences are there in the response spectrum and the design spectrum. The design spectrum is based on statistical analysis of response spectrum for the ensemble of ground motions. So what you have to do is, if you are constructing a design spectrum, you have to take a number of ground motion and do the statistical analysis. Okay. Statistical analysis for the ensemble of ground motion. Okay, so ensemble here means set of ground motion. And it assumes that the ground motions are may originate from different earthquakes from different earthquake faults. So let me mention here from different earthquake faults. This is the right term. And everyone has every fault is characterized by its magnitude or the highest magnitude. And the distance that is important, like the site to fault distance. Okay, so the response spectrum for each ground motion is computed, leading to as many spectral values at each period as the number of ground motions. So when you develop the response spectra for a number of ground motions, so you can have a spectra like this, you can have something like this, you can have something like this, you will have a huge number of spectra of various characteristics. So at a given time period, at a given vibration period, you will have values equal to the number of records. For example, if you have selected 6 record or 7 record or 20 records, so for a given time period, you will have 20 different values. When you take the mean, it just become like this, and then it give you a variation if you are interested to know the mean plus 1 standard deviation. Okay, so statistic analysis of these data provide the probability distribution like this for the spectral ordinates. So it's mean value and standard deviation for at each time period. So connecting all the mean values gives the mean response spectrum. So if we connect all the mean value, we get the mean response spectrum. So it is evident that the shape of these response spectra is much smoother than the response spectrum for any individual ground motion. So for example, if you look at this, and everyone will be jagged response spectra like this one, okay, or like this one, but when you combine them and take the mean, it becomes a smooth response spectrum. Now, this kind of idealized spectrum provide the basis for procedure to construct design spectrum. So if you look at this dashed line here, this is providing you the simplified or idealized design spectrum. Okay, now this is the way how to construct elastic design spectrum. Okay, drawn here are the peak acceleration value, peak ground displacement, and the peak ground displacement, peak ground velocity. Now remember that for a number of records, for a number of ground motions, these peak values, these are basically the average values of all the records. Okay, and when you obtain the mean spectrum, so this is what you can obtain. Okay, so this is the elastic design spectra. This is what you see, the TA it is exactly like the ground acceleration. From TA to TB, it increases linearly, okay, up to the acceleration value multiplied with the, like multiplying ground, peak ground acceleration with the amplification factor alpha A, and that amplification then constant till the TC. Then between TC and TD, the amplification factor is alpha V, and if that is multiplied with the peak ground velocity, you get the velocity here, the value of the velocity or the pseudo velocity, and from D onward, the uh, the displacement can be obtained that is related to the displacement that is obtained by multiplying the ground displacement and with multiplying ground displacement by the amplification factor alpha D. Okay, and these factors can be, these factors like TA, TB, TC, TD, TE, TF, and also alpha A, alpha V, alpha D, they can be obtained from the statistical analysis. You can also just plot the acceleration spectrum, pseudo acceleration spectrum. Okay, this will give you a different shape because in this case it is just showing you acceleration on the y-axis and the vibration period on the x-axis. These are the two quantities only. Okay, but again it can give you a clear description of the acceleration demand, pseudo acceleration demand that you can use for calculating the static force or the base shear acting on a single degree of freedom system. And from there you can have a look at the acceleration sensitive region, the velocity sensitive region, and the displacement sensitive region as well. And these factor like from the ground displacement, from the ground acceleration to the maximum acceleration, the factor is 2.71. It depends on the statistical analysis. How these two are varying also depends on that. The same as this region, the decrease from this value to this value depends on the, again, the number of records used in the analysis. So, so that was in a log-log scale here, and you can plot the same also on a linear scale. On a linear scale, this is how it will look like. Okay, so these are the acceleration response spectra for various damping values. Okay. Okay. So we need these elastic design spectra to obtain what is called the peak structure response. So the peak response of an SDOF system can be determined readily from the earthquake response or the design spectrum without computing the response history. So the advantage of the design spectrum is that you don't need to carry out the elastic time history analysis of the system or response history analysis of the system to obtain the demand. You just need to go to that spectrum, uh, knowing the vibration period, you can quickly obtain what is the peak values or the peak demand. Okay, and then all the response quantity and seismic demand can be expressed in terms of the D, V, and A, which depends on and the mass and stiffness of the system to obtain the other peak demand on the structure. For example, if you look at the displacement that we can obtain from the spectrum, there is D, which can be related to velocity or the pseudo velocity as T n over 2 pi, and also to acceleration as T n divided by 2 pi whole square into A. Okay. Also, the peak value of the equivalent static force because ultimately we need these response quantities for calculating the equivalent static force. FSO that is equal to KD, or it is equal to MA, or we can also write as A by G into W. So knowing stiffness and this deformation, you can calculate or mass time acceleration or A by G into W. So then you can carry out the static analysis of the structure subjected to this lateral force to provide the internal forces, for example, shear, moments in columns and beams, and stresses and so on that can help in the design of structure. So in particular, what we obtain, as I mentioned earlier, is the base shear that is equal to A by G into W, and the overturning moment is H over VB naught. For example, if this is a single degree of freedom system, single story structure, acted upon by FSO, this will be the base shear and this will be the MB naught. Okay, if this is the height of this system. So if you look at the three spectrum that we discussed, acceleration, velocity, and deformation. So deformation was the response spectrum, and then the pseudo velocity and the pseudo acceleration response spectrum. So you can, if you have one of them, like deformation, velocity, or acceleration, any of them can be used, and it is sufficient for computing the peak deformation in forces required for the structure design. So in practice these days, what we need is, or what we do, we just develop the elastic design spectrum, and that is sufficient for the design of our structure. So by this I conclude my second lecture. If there's any question you can ask me, otherwise we can conclude.
Yes, sir. Assalamu alaikum, sir.
Yes, please.
Hayatullah, sir. Sir, zama question da چې منګه وایو چې دا ډیمپینګ چې دا ویلاسټي ریجن افیکټ کوي کنه سر جی لکه منګه کال تمالو نو ډیمپینګ ریشو چې موږ د ویلاسټي سره لري او منګه دلته وګورو په دې ریسپانس سپیکټرم کې نو منګه دا فکس ډیمپینګ ریشو لپاره مختلف ریسپانس سپیکټرم د ډیسپلیسمنت لپاره هم ډیولپ کړو د ویلاسټي لپاره هم ډیولپ کړو د اکسلریشن لپاره هم ډیولپ کړو.
Okay.
Yes, sir. Clear, sir.
Let's have a look at this. I don't know, I didn't get your actual point, but let's have a look here. So this is what you are referring to?
Yes, sir. Sir, my question now چې موږ چې کوم دا damping ratio دی کوم چې موږ اوله کې equation لیکلو په lecture number 1 کې.
Okay.
like displacement او acceleration لپاره موږ damping ratio نو لیکلو خو موږ صرف د velocity سره لیکلو چې او البته تاسو چې هغه لاست کله lecture کنکلود کوو تاسو البته دا سیمو وي چې زموږ سره چې دی نو damping چې دی velocity region چې دی هغه زیات افیکټ کوي.
Yeah, of course, that is true.
خو موږ دلته وګورو سر جنو که موږ پرس د ډیسپلیسمنت یا د ډیفارمیشن لپاره ریسپانس سپیکټرم ډیولپ کړو د هغې لپاره ډیمپینګ ریشو فکس لازمي سره هغه موږ
Yeah, of course you are right. We have to velocity is mostly affected by damping or largely affected by damping, but it doesn't mean that we have to ignore damping in displacement and acceleration. We have to consider. Okay, there is no way. But the fact is that the velocity sensitive region is more affected as compared to displacement and acceleration. I mean, look at this. Wait a second. Okay, these are the elastic acceleration response spectrum. Okay, and you can see that if you change damping, the spectra is changing. You can see the values are lower. It is just in this, maybe in this very short period range where the damping is not having any effect on the acceleration, but in the other region it has a lot effect. And also, if you compare some maybe some far region here in a very long period, so it can have less effect, because look at here, it is affecting more these region, this and this, as compared to this region and the regions over here. But it is the, you have to consider the effect is there.
Okay, sir. Thank you, sir.
Okay, so if there is no any other questions, so I will conclude at this point.